Morning, everyone. Thanks for joining us this week for another Fireside Chat with the Experts. Today we're doing a Q&A. We've had several questions over the last few weeks on our topics that we've covered. We weren't able to get to all the questions, so we just want to take a break through going into these new topics and answer some of those for you. So we have today Dr. Bill Cardoso, our CEO, and Dr. Glen Thomas, our VP of Technology. So we're pulling out the big guns, lots of knowledge here, lots of experience with X-ray. So we'll be diving into these questions for you.
He was talking about you, Glenn, when he said big guns, by the way.
Yeah, okay. Yep. We'll
Not
see.
Omar.
We'll see how stumped we can get.
Sounds
You should
good.
call the segment Stump the Chumps. That'd be fun.
There you go. So our first question, what are the differences between open and closed X-ray tubes?
Open and closed X-ray tubes are, that's a consistent question that we get on a regular basis. You have to go back to the basics of why an open X-ray tube was designed. And it all starts with the physics of X-ray, right? We can bend the rules, but the rules are always going to be there. And the rule is you can have 1 watt of power per micron of focal spot size. Focal spot size gives us the resolution because it's a pin source, right? It's a point source, just like a flashlight or even the sun. It's a point source. So that is the point that the X-ray or the electron beam hits the target anode and reflects. So with that 1 watt per micron limitation, in the late 60s, they were running into some problems in industry that we were trying to see through jet engine impellers and jet engine components, right? And we needed the resolution to see some of those welds. The problem was that to get past that 1 watt per micron of focal spot law, essentially, we would have to open up the focal spot to the point where you were less resolution on your X-ray tube than the requirement of the application, right? So some really smart guys got together and designed an open X-ray tube, which is essentially all X-ray tubes have consumables. The consumable is the filament, which is where we burn the electrons off of the filament, just like a tungsten light bulb. And then we have the anode, which is the point that we have the electron beam coming from the filament hitting the anode, producing photons. You have about a 3,850 degree temperature at that point. And that's the main reason why we can't exceed that wattage, because it will start melting holes in the tungsten. So essentially, to be able to pull that off reliably, pull that heat off, because 98% of X-ray energy that's produced during making an X-ray image is heat. So we had to pull that heat off very quickly. To get around that concept, they decided that it would be a good idea to make those consumables replaceable by the operator. There are some other schemes in medical applications that we do the same concept as far as saving the focal spot and being able to apply a lot more power to the focal spot. But that's just, again, another way to trick physics, right? So the concept there was we could take an image and we can take a very high power image, say 10 watts per micron, and we can intentionally destroy the X-ray tube. We can destroy the filament and we can destroy the anode. So an open X-ray tube is designed to be field repairable by a fairly experienced or trained technician. You'll get a lot of rhetoric about, oh, it'll last forever, and you just got to change the filament, and you just have to change the anode. It's an easy task if you have the training to do so. So essentially, this X-ray tube was designed that would vacuum itself down every time you turn the tube on. So you would take an image, you would get a 2-minute shot, and you would just totally destroy the X-ray tube. But they were accomplishing what was needed, and what the requirement was, we need high resolution images of very heavy, dense components. So that was a success. The open X-ray tubes have a lot of ancillary subcomponents that no one ever seems to mention. They say, oh yeah, this tube will last forever. You can change the filament and rotate the anode, right? What they don't tell you is you have a turbomolecular pump, you have a roughing pump, you have a high voltage component that's almost in some cases larger than the cabinet itself, as well as a cooling system to cool the tube, right? Because if we're pulling out all of that heat and we're intentionally creating a lot of heat, you can literally destroy the X-ray tube housing, you can melt it. So we still have to pull off a real large amount of heat fairly quickly. So in a closed X-ray tube is essentially that. It's an X-ray tube that's vacuumed down during manufacture to about 10 torr as far as pressure. The X-ray tube has a fixed filament. It has a fixed anode, as well as, in most cases, a lot of focusing grids, or essentially magnetics that focus that electron beam to a really fine point. Service-wise, there are no service, end-user serviceable parts. An open X-ray tube, you have the filament, you have the anode, you have O-rings, you have greasing of the high voltage components like the wells for the high voltage cables. So there's all kinds of different parts that have to be maintained. Closed X-ray tube, it either works or it doesn't. There's not really much that's a user serviceable issue, but they are highly reliable and they are somewhat maintenance free. We get a lot of complaints or questions that says, well, I have to replace the whole tube when it breaks. Yes, a closed X-ray tube, you do have to replace the complete housing, the complete tube, the high voltage, say in 5 to 7 years, 10 years, depends on your usage. Because if you remember, every X-ray tube has consumable components. Every time you create X-rays, you're pulling electrons off of that tungsten, just like a light bulb in your house, and you turn on a tungsten light bulb. So it's eventually the X-ray tube, the closed X-ray tube, will die or will become unusable due to the pitting of the anode itself. So you get a really bad X-ray image. And it happens so slowly over time that you don't even realize it. If you walked in, the operator's using the machine, and unless he's using IRQs or image quality indicators, he really has no clue that it's degraded to the point that it has. And you walk in as a service guy or even a sales guy, and you look at it and you're like, wow, what's up with that? And they're like, what? So, but over a 5 to 7 year period, you will probably have to replace the closed tube. Yes, they are fairly expensive. Could cost tens of thousands of dollars depending on the tube. But when you look at the individual maintenance and downtime and the expertise that it takes to service an open X-ray tube, the costs are pretty close to the same, right? So you pay a lot more money up front for the ability to have a lot more service issues with an open X-ray tube. And a closed X-ray tube, you pay a fair amount of money, but you have maintenance free for 5 to 7 years, right? One of the major disadvantages of that X-ray tube is if you don't really know what you're doing and you get some dust in there. So in a dusty environment or a production environment, one speck of dust would be enough to destroy an open X-ray tube. Problems you have with open X-ray tubes is when if you get a fingerprint or you get dust and you fire that thing up, you're going to create carbon tracks. That X-ray electron beam is going to find a different place to land other than the anode that you expect. And when it does that, it could pit the interior of the X-ray tube to the point where it's now unusable. You have to buy a new one. A single fingerprint inside of an open X-ray tube will destroy the tube forever. It's impossible to fix that. The oils in your skin will create an arc and you will have a major issue. The only advantages of an open X-ray tube in the last few years is when you use it in electronics, you can get high magnifications. And that is the main reason for that is we can direct that electron beam to, say, the window of the X-ray source. Typically, we would use an anode made out of tungsten, and that anode is embedded in a copper substrate, a bar, and essentially that bar is grounded and it has a heat sink on the end of it that's immersed in high voltage oil, right? When you look at the open X-ray tube, we can actually aim that electron beam at the window, and we can use a diamond and we can use some other exotic windows that create the X-ray photons at the window. And what that does is that allows for extreme magnification on the X-ray source. So in applications like electronics, the only reason to go with an open X-ray tube would be if you needed extreme magnifications. And being kind of a capitalist world, closed X-ray tube manufacturers have made some really unbelievable X-ray tubes in the last few years that rival the magnification of an open X-ray tube in a closed tube package. So you get all of the advantages of an open X-ray tube for a general operator. With electronics, you're never going to overdrive the X-ray tube intentionally. So you get all of the advantages of an open X-ray tube as far as magnification, and you get it in a nice compact package, which results in a smaller cabinet in the X-ray and a smaller overall footprint of the X-ray system itself, because you don't have the external coolers, the external high voltage requirements. So it's just, open X-ray tubes have their place, but in my opinion, open X-ray tubes really don't have a place in electronics unless you're looking at high magnifications. And, we're eliminating that as well.
Yeah, I think that's been a huge improvement or development over the past few years, is that transmissive closed tube source. That's being and just for some background, on a closed tube or even in an open tube, you have two different processes to generate X-rays, right? You can have your target, your anode. It can be on an angle like this one. Pretend my phone's a target here, and you have what's called an electron gun, or the filament that's going to warm up and generate free electrons. Those electrons get accelerated, and when they hit the target, you have this shower of X-ray photons getting out of the source, right? So X-rays get generated here. They go super fast, hit the target, and there's something called brainstorm radiation. So the electron is moved out of the shell, and then when it goes back to its shell, it emits this X-ray photon. So that's called reflective tube, because you can see it reflects. There's a reflective motion to generate X-rays. And then what Glen is talking about is the transmissive. So the window that provides that vacuum seal of the tube. So this is the outside world. This is inside the tube. Instead of reflecting, what you do is you put the target at the window, and you shoot the electron beams right at the window, and on the other side, you have X-ray photons coming out. So what does it matter, right? Because this method is really, really, really hard to make. The reflective method, it's been around since the late 1800s, 1900 was just a few years ago. 1800s, that's what Röntgen was playing with when he discovered X-rays in the first place, right? The advantage of reflective, right? It's been around for a while, because here in the back of the anode, usually gonna see a chunk of copper, a chunk of metal, to cool off this side of the X-ray tube. Why? Because as you have, as Glen was saying, right, as you have a lot of electrons hitting this target, it's going to warm up, right? It's going to create a lot of heat, and you have to dissipate the heat. If you don't, you end up putting a hole on the target, and that hole is going to screw up with your resolution. Why? Because out of this target, you want the X-rays to get out of here in a perfect cone, right? Every line going like this, going like that, but perfect. So that target ideally is a point in space. If you start warming up with because of the temperature, the stress of the material of the target, what happens is that that's not a point anymore. Now it became an area, and in that area is going to happen is this electron comes this way, one X-ray photon goes that way, the other one goes that way, and as a result, you end up with a fuzzy image. So the edges of your image are not as sharp as they could be. This is the difference between mini focus or micro focus or a nano focus X-ray source. The smaller the target, the better the resolution, the lower the power that you can run. Like Glen said, if you want to blast a lot of power, you're not going to have a tiny target anymore, right? It's going to warm up and increase your, make your resolution worse. So there's a lot of heat here, right? So if you take this target and you put at the window, you want this window to be as thin as possible. If you have a thick window, you know, a block of copper to cool off the target, you're not going to have any X-rays coming out, right? They're going to be shielded by the window itself. So you need thermal dissipation, right? Low impedance thermal path from the target to your cooling heat sink. And at the same time, it has to be really thin. Ideally, no matter at all. So that is a big challenge that X-ray source companies have been working with the past few years. And diamond is one of the materials that fits that profile of being good for heat dissipation. It's very strong and you can make it very thin, right? So it doesn't shield the X-rays that you're generating. And so what does it matter? What does it matter if it's a reflective source or a transmissive source, right? I mean, why go through the pains of making a transmissive source with this exotic window? Because can you imagine, you have to hold vacuum here, right? So you have the box of the X-ray source, and that's my little window that is this target, and at the same time has to hold vacuum. What happens when things warm up? They expand. What happens when they cool off? They contract, right? So this has to keep vacuum at the same time that it has to stay stationary in one place because you don't want your target doing this, right? And it has to hold vacuum while expanding and contracting because of the heat that's being generated here. So not an easy mechanical object to build. It matters because of magnification, right? Glen also mentioned magnification. Magnification, if you imagine you have your source here, okay, on my window, the sample is going to be sitting on top of the source, and then I have my sample, and then the sensor is going to be, you know, on the other side of the sample, and the X-ray image is going to be the shadow of my sample onto the sensor. The magnification is going to be, so M for magnification is going to be 1 plus the distance between the sample and the sensor is the numerator, and the denominator is the distance between the sample and the source. So what does that mean? So it's 1 plus this distance divided by this distance. What does it mean? It means that to magnify, I have to bring my sample as close as possible, right? As close as possible to my source. Now, if my source is like this, and that point is several, you know, maybe half an inch away from where the window is, that's limits how much I can magnify my image, right? Now, if my target is now 300 microns behind the window, or half a millimeter, right? Now I can bring my sample, place right on top of the source, and achieve very, very high degrees of magnification. So this transmissive closed tubes have really allowed us to provide kind of the best of both worlds. Really high mag because it's a transmissive source, and at the same time a closed tube, so we can offer low maintenance X-ray source. And so nowadays, if you'd ask us, when do we use one or the other? Because we've used both, open tubes and closed tubes, they have their place in X-ray applications. For the high mag, in the past we use an open tube. Now we're using this transmissive closed tubes because they're just easier to use, and we don't have to be worrying about the two vacuum pumps and a high voltage block and in a cooling system for the tubes. It's much simpler, much compact, and make things much easier to for the operator and for the user. And we leave the open source nowadays for the high power stuff, right? When you get to the 225, 300 kVs and up, we're going to be talking about an open tube application, because at that level, at that amount of power, there's no diamond enough today that can pull that kind of power. Now you're going to be discussing rotating anodes. We're going to be talking about a chiller that can pull quite a bit of heat out of the source.
All right. Thank you, gentlemen. That was a lot.
So is that question one?
Reflective or transmissive as well. So.
Well, that was we were summarizing, right, Glenn? So,
exactly.
I think you had at least 3 questions there.
Right.
That's good. Well, we got 8 minutes, so I'll give you a simpler one.
It's got to be a yes or no question. Otherwise, it's going to take longer than 8 minutes.
What's the difference, practically speaking? Right? What's the difference between kV and MA, kilovolts and amps, milliamps, microamps in a source? What does that practically mean when a customer is designing a system?
So that's another one that could be a long conversation, right?
We'll make this one long one.
Hey.
Yes, there is a difference.
There is a difference. Done.
So if we look at KV and MA, and an easy way for a layman without getting into the physics is to think of a garden hose, right? Consider the X-ray tube the same as a garden hose. We're projecting photons, and in this case, a water hose is projecting water, right? So if you look at the KV would be the pressure, the amount of pressure that pushes the water or the photons out of the hose, right? So the KV gives you the ability to penetrate items. The higher the KV, the better, and the faster the photons are going to be, be able to traverse through the sample. So KV is the penetration. That's the power behind the electrons and the photons. MA, if you think of the water hose analogy, the MA would be the diameter of the hose, the amount of water, or in an X-ray tube, the amount of photons that make up the X-ray beam. Because we could essentially have an X-ray beam that's 150 kV and 1 photon, right? You will get a small blip on some screen somewhere, but you won't be able to create an X-ray image. To create a usable X-ray image, you need to have the proper amount of penetration, which is the KV, to be able to penetrate the part, and you need enough photons to actually create an image. If you think of that, you think of a dot matrix printer, right? In the lack of photons would be the same as if you had a dot matrix printer that was putting out, or even worse yet, the 9-pin printer of the 80s, right? You'll get a definite...
Maybe doesn't know what that is, Glenn.
You'll get a definite degradation of the image. So the MA gives you more photon statistics, the ability to light up the image detector, whether it's a film, digital detector, image intensifier. Regardless, the MA gives you more photon statistics. It puts more photons on the image. And then it goes back to that physics concept, is we still have a wattage issue, right? So if we have typically in an electronics X-ray system, pretty standard is 9 watts of power. right? So that gives us the ability to do 100, say 90 kV at 0.2 MA, right, is a good number, 0.256 MA. So we use very low MA, so we have the ability to maintain that focal spot. A lot of X-ray tubes are isowatt, which means that they are limited in wattage. You can't overdrive the X-ray tube. If you crank up the kV to a real high point, the X-ray system will drive down the MA to maintain a stable wattage that stays within that safety threshold of the X-ray source and the X-ray tube. So in some cases you would want to, in a lot of cases, you're not using the full kV of an X-ray source. Your optimum kV is somewhere in between 0 and the full maximum power. So with that, you get a happy medium in kV, which is the ability to penetrate the part. Because if you over-penetrate the part, you start losing artifacts, or you start losing, details in the actual X-ray image. So there's a fine point where kV and MA make a difference. If you over-penetrate the part and you don't have enough kV, you could still get an image, but it's going to be a very grainy image. It's going to be featureless for the matter, So what you want to do is have a happy medium of kV and MA. And through algorithms, back in the day, you had to be fairly fluent in X-ray to understand how much kV and MA. A practitioner like an RT in a medical industry, they're really good at knowing what that kV and MA is going to come out to. They make those determinations fairly quickly because their samples change. They may be doing an elbow or a wrist, but each individual has a different density, so they will make those changes on the fly. And they're pretty highly trained at being able to make those judgments. Used to be X-ray, industrial X-ray was the same thing. Back in the day when it was all film and you only had one shot and one chance, so you would climb up on a bridge or you would climb up on a tower, essentially they would stack the film and they would run multiples. So they would stack the film and you would do one X-ray image at say 1 MA, 10 seconds at 100 kV. And then they would pull one off the film. And since film is accumulative, they would continue to add time and kV and MA adjustments to get a bunch of exposures, right? So they would have a lot of different exposures in this one shot, and they were up in the air, so they would come down, and then they would pick the best image out of, say, 10, right? So that kV and MA adjustment is somewhat tricky. And one thing that we've done to eliminate some of those issues for an operator is the WISE software that we have. It adjusts kV and MA, and it adjusts brightness and contrasts, and has some algorithms that will give you the ability to make those changes seamless. The software looks at the exposures and looks at the grayscale values based on the histograms, and will make those adjustments for you. So all you really need to know if you're an operator is kind of the basics of what they do. And the main reason for that is you get a general idea of what kV you need to not over penetrate the part, and you let the X-ray system and the software make those other decisions as far as how much brightness, contrast, exposure rates, and the MA it's needed to accomplish the goal.
Nice. Thanks, Glenn. Right on time. It's 10:30 on the dot. Must be watching the clock.
Yeah,
well,
we can keep going.
He's done it before, David.
Well, we have a long list of questions, so we're going to continue this next week. I want to keep these to half an hour for you guys, as we said we would. So if you have any other questions that came up today, or questions you just want answered in general, if you're watching this on YouTube later, you can leave a comment below. Or you're welcome to email us at info@creativeelectron.com. Thanks, Glenn, appreciate it. Thank you, Bill, for your time.
Thank you, guys.
And
Thanks.
please join us again next week.
Thanks. Take care.
All right, bye.
Play which one?